Hello and welcome to the Storage Developer Conference 2021. My name is Jerome Gaysse. I'm Senior Technology and Market Analyst at Silinnov Consulting. I provide technology report services related to emerging storage and computing technologies with a huge focus on computational storage. I follow this new trend from the beginning, and I am very happy to see how it is moving. The purpose of my talk today is related to the building blocks to design such devices. I will try to help you in considering the available technologies on the market and how it can change the future of data center, especially on the IT carbon footprint. Before going in the details, let's spend a little time on the definition of what is a computational storage device. The SNIA specification defined three devices. The first one, the processor, or CSP, which is a kind of processing unit on a board, like an FPGA board, that will be integrated in a system very close to the storage, with some kind of direct accesses between the board, the computing board, and the SSD without involving the host CPU. The second one, the drive, or CSD, it's where you have both computing and storage on the same board, where the computing part will be done in a specific SSD controller or with a specific coprocessor. And the last one, the array, or CSA. This is at the system level, where you integrate a processor, a CSP, and or the drive, a CSD, and standard SSD. Computational storage is well known to reduce the data movement between compute and storage, leading to a lower latency and a lower power consumption. If you want to design a computational storage system or device, this is because you want to solve a problem in terms of performance, power consumption, density, security, or all of them. So the way you will design it, and then the way you will take decision on the technologies to be used, really depends on the problem that you want to solve. So, what are the available technologies on the market? How to select it? Then, let's have a look on the computational storage ecosystem, and we will try to. It is very interesting to analyze the computational storage ecosystems. In fact, this is a mix of already existing ecosystems. I mean, it's a mix of computing, storage, and even networking ecosystems. So it's very huge, also in terms of kind of technologies, from IP to NVMe, so the memory chip, processing chip, software, board, and systems. So you have everything that you want. On this slide, I will not put all of the company's logo that will be involved in the computational storage, but few names in terms of IP or processing unit, for example, with ARM and Xilinx. So you have everything on the market for CSP and CSD, so really the building blocks for that. On top of that, we have a new and emerging ecosystems, which is in fact the already available product on the market, CSD or CSP, for computational storage. Few examples: NGD System, IDTCom, Samsung, and Scaleflux. Just few of them. And you can use this already available product in a system design for your applications. So if there is nothing really new on the building blocks. That's very good news, because that means that you have everything that you want and you know everything, and so you are able to play with it. So we just reviewed the computational storage technology and ecosystem, and it's very big and we can find everything that we need. So which one to use? And maybe the first question, a custom design or a commercial product? Like any system, we can wonder, do I build it from scratch, or may I use an existing product which is available on the shelf? As an example, for a CPU, am I doing my own ASIC design, or can I buy an existing CPU? You will know this question, where you have a trade-off between the development cost, the development time, and the return on investment. For computational storage, these trade-offs apply. But there are also other considerations which are specific to computational storage. With a custom design, you will get an optimized platform because you are able to perfectly design the reduced data movement between the storage, the right storage, and the right compute. And your added value will be at this hardware layer, but maybe also at the software layer. With a commercial product, so you can integrate it immediately in your system, so you save time. And maybe you will spend more time on the software development, and this is where you have your added value at the system layer. If you want to design a computational storage device, this is because you want to bring a high value at the system level. This is your added value. In your design flow, you absolutely need you to use a simulation tool at the system level that will help you to estimate the benefits in terms of power consumption, total cost of ownership, density, and even the carbon footprint. If you just focus at the computational storage device level, you can show great benefits in terms of X factors. But I think it's more relevant to analyze the benefits very close to the end user. Then you may lose an order of magnitude in terms of X factors, maybe leading to just a few % of benefit. But this is the real benefit for your customers and for the end users. At the beginning of the year, I had the great chance and opportunity to share the results of a simulation I did with my own tool on an hybrid computational storage system running in a cloud environment, running about 1,000 VMs with database. The benefits I show in my simulation is -7% in density, -15% for the TCO, and -25% in terms of power consumption. Let's spend a few more time on the system benefits and especially on the carbon footprint reduction. When I submitted my proposal to the SNIA committee, I did not plan to talk about the carbon footprint reduction on this talk. But after spending a few times this summer on the understanding of a carbon footprint analysis, I realized that this topic needs to be discussed today, and it needs to get more consideration because computational storage can bring more value than we can expect on that. You will understand why. So, when we design a computational storage device, this parameter, this input, must be taken into account. So, we all know the computational storage benefits as I just described, but when we often focus on the power consumption reduction as a direct and unique link with the carbon footprint reduction. Again, 25% in my example. Does that mean it is 25 reduction for the carbon footprint as well? No. Using computational storage can provide really more benefits for the carbon footprint. In case you are not familiar with the carbon footprint and how we can measure it, in fact, it measures the energy spent for the use, okay? The watt. But it also integrates the energy used for the manufacturing, the transport, and recycling. So, when we design a computational storage device with a higher density, because you integrate compute and storage on the same board, on the same system, you also reduce the energy used for the manufacturing or the transport and for the recycling. So some estimation I did is that you can reach a reduction of 50% on the carbon footprint by using computational storage compared to a standard IT architecture. It's awesome. Now we can go on the review of the building blocks for the computational storage device. Let's start with computing, because this is where you have the widest choice, because you can use a FPGA, a system on chip, a DPU or GPU. First, the FPGA, which is a component well used in computational storage devices for both CSD and CSP. It provides a very good ratio in terms of performance and flexibility. It can address multiple interfaces like the non-flash, the network, NVMe. On the non-flash side, with the on-fee interface, for example, you have a direct access to the non-flash component, so very efficient in terms of latency between storage and compute. It can address both application acceleration and storage services for the workload. Also a good reason to select an FPGA for your system. This is because you want to bring added value at the hardware integration, so at the RTL level. And then for the next generation of products, you can move to an ASIC for power, cost, and mechanical improvements. The difficulty with FPGA is the complexity for the development, for the programmability, and the power consumption. The system on chip, more easy to use in terms of software development, of course, because it will integrate standard CPU cores, so you have all the software environment for that. It also provides interfaces with network, NVMe, and non-flash, like any SSD controller. Another benefit is on the mechanical constraints and the power consumption. So if you want to design computational storage for embedded devices with M.2 form factor, yes, that's the perfect chips to select. And if you want to get specific application acceleration, so maybe you will move to an ASIC development. Okay, there is a higher cost for that. But in terms of performance optimization, that will be great. There are some computational storage devices available on the market with some specific video acceleration, video processing acceleration, which is typically used for video streaming applications. The DPU, so data processing unit, here I mainly refer to devices which are used for the smart NICs. So that will be chips between the network and an NVMe interface. The interest for that, so you will integrate this kind of product more in the CSA level, and you can use it to do some computing on the fly where you have data coming out or in the system. So in terms of workload or applications, that will be more for storage services like encryption, compression, dedupe, and replication. We can also imagine use case where the computational storage can be used for a recording system with packet processing features. And finally, the GPU. When we are talking about computing, we need to talk about GPU. But in fact, for the computational storage landscape, GPU is not the preferred choice today. This is mainly due to a lack of direct interfaces between storage and the GPU. Even if there is the GPU direct concept, maybe in the future we will see GPU in computational storage array, but not the real direction today. And I think this is because GPU are very power hungry. So you may lose the benefit of the power consumption benefit of computational storage because you will spend the power budget in the GPU itself. But in terms of applications, if you have some good use case for that, of course, that will be for video and image processing or for artificial intelligence. In the memory landscape, computational storage is obviously based on the use of non-flash. For the latest CSD product on the market, the trend is even to use QLC, since it comes with the highest density. So we can find few terabytes of memory directly coupled to the embedded computing in the CSD. If you are considering a full system design with the use of CSP attached to SSD, then you can play with different non-flash technologies, still using QLC for the density, but why not using fastest SSD, which are using TLC or MLC? There are also opportunities to use an MRAM in a computational storage device for a write cache function, okay? But also maybe for more specific applications. And I think about a deep learning system. If you want to provide deep learning acceleration, not with a GPU, but with a specific ASIC or FPGA on your board, then you need to store some parameters. Why not using the MRAM to store the weight of the neuron model in your device? And finally, 3DXP or any other similar technologies like resistive RAM may be used as well, but it's very emerging memory and there is a limited number of providers. So not the right direction today, but in the future, for sure. On the interface side, computational storage devices are based on the NVMe protocol. That's obvious because the latest high-performance SSD are coming with the NVMe interface. And it was the easiest way to design computational storage by hiding computing in such SSDs. And for the management, for the computational storage commands, we can use the NVMe protocol differently. For example, we can use vendor-specific commands, which are available in the NVMe specification. Or we can use the different namespaces with some different action. For example, one namespace for an acceleration algorithm, or another namespace just for the compression, and so on. NVMe over Fabric is just the extension of the NVMe over the network. So very similar in terms of theory of operation, but allowing a more disaggregated architecture. As network-attached SSD are coming to the market, I'm sure that we will see in the very near future computational storage devices with this NVMeoF fabric in the design as well. And the third one, CXL, or any other new interconnect with cache coherency. It is definitely the highest level of integration. In addition to get reduced data movement between compute and storage, you also have a direct access between the host CPU and the CS device. So in terms of overall benefit and performance, wow, that's the ideal choice. So as soon as the CXL market will arrive with product CPU and system, for sure we will see computational products with such interfaces as well. And finally, software development. Not too much details on this slide, but for sure software for computational storage is the most difficult part of the design of a device. The integration of storage, compute, network at the hardware level is quite easy. But developing the software that will manage everything is much more complex. In addition, since it is a full system architecture change, the integration with a standard operating system, hypervisor, or application is definitely the key of success for the design. It is a trade-off between standardization and performance optimization. Hopefully, the SNIA specification will help for that. On the other hand, this complexity for the software layer, this is definitely where you can bring your added value. Of course, for CSD and CSP products, you will need to manage the internal orchestration. But at the system level, you will also have to bring your software that will manage everything. So a very good opportunity to bring high value in new system design and a lot of innovation as well. As a conclusion, we are entering a very exciting time for architecture design. We are just at the beginning of computational storage, and I really think that it will change data center infrastructure. Maybe we will start with just few storage services, acceleration, encryption, compression, and few but very important applications like database and machine learning or video streaming. But for sure, it can come the standard way to design any new system in a data center in the future. So there are huge opportunities to bring innovation and added value in a new system design at the hardware and software layer, and especially with a focus on carbon footprint reduction. Designing innovative computational storage devices with better performance, lower power consumption, a higher density, a longer lifetime is definitely an answer to go on a real green IT strategy. Thank you very much for your attention. I hope you enjoyed this presentation, and I hope you learn about computational storage design. Do not hesitate to contact me if you want to talk about computational storage or any new technologies. Thank you very much and goodbye.